Picking up from our last class, meth for alkane will be methane, meth for alkyl will be methyl, and so on and so forth. And we also looked at benzene, the special aromatic molecule that we are going to see many times in this course. With one hydrogen missing in benzene, we call it a phenyl. PH, Phi, or AR are the abbreviations. Okay. So there is a variety of aromatics there, but we will only be focusing on the benzene and the toluene. So we had looked up that there is a benzene with all carbons being sp2 carbons, and then to this sp2 carbon, another sp3 carbon is attached. All of these are sp2, 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 sp2. But this is the only sp3 carbon. And if you remember your bond line structures, each dot is a carbon. And if nothing else is there, you have to remember that carbon makes 4 bonds. 1, 2, 3, 4. What is the 4th bond? It is the hydrogen. How many bonds this carbon is making? It is already making the 4 bonds. So you don't have to fill in any hydrogens here. But this carbon right here needs all the 4 bonds. 1, 2, 3, 4. So 4 electron domains or electron densities, that equals sp3. So this location is the benzylic location, also known as the benzyl. So this carbon right here, which is outside of the benzene ring. And this carbon in the benzene ring will constitute your phenyl. Any questions so far? Okay. So even though we don't consider alkanes as functional groups, we still have to classify them as primary, secondary, tertiary, and quaternary. What does that mean? So if you look at a general carbon structure, so how many carbons do I have in this? I have 4 carbons. Now I don't need to draw all my hydrogens here because it is known, it will be understood that all the remaining bonds will belong to hydrogen. Any questions on why I just wrote 4 carbons and not the hydrogens? Okay. So when you say primary, secondary, and tertiary or quaternary, let's look at this particular example right here. This carbon, which I'm going to label as 1, is attached to how many carbons? This carbon is attached to only 1 other carbon. And hence, I will label it as a primary carbon. Similarly, if you look at this last carbon, so 1, 2, 3, 4, this particular carbon, carbon number 4, how many carbons is that carbon attached to? Anyone? Okay, once here. Elizabeth, are you here? Elizabeth Chapman?
Excuse me, I have a question.
Please go ahead.
I'm sorry.
Yes, go ahead, Yana.
Oh, okay. I was trying to figure out, so for this, is it just simple memorization or is it application as well?
This will be application also and memorization as well. So you will have to memorize that every time a carbon is attached to one other carbon, it will be a primary carbon. So how many carbons this carbon is attached to? This carbon is only attached to one other carbon. So we will label this carbon also as a primary carbon.
Okay.
So it's going to be both memorization a little bit and then applications a lot.
Okay, thank you.
You're welcome. What about this C2? How many carbons this C2 is attached to? It is attached to two other carbons, which is a secondary location, making this carbon or classifying this carbon as a secondary carbon. If you look at
So
carbon,
because, I'm sorry. So
go ahead.
because that carbon right there is attached to two other carbons, that carbon alone is a secondary carbon?
Yes.
Okay.
Yes. And if you look
Okay,
at
thank you.
C3 also, the C3 is also attached to two other carbons. And so we will label this also as a secondary carbon. Okay. So interestingly, all the hydrocarbons with a carbon or a nitrogen on them. Why carbon and nitrogen? Both of them are multivalent atoms. Carbon can make 4 bonds, nitrogen can make 3 bonds. So with multivalent carbon and nitrogen, we will have to classify them as a primary, secondary, tertiary, or a quaternary. So a primary carbon is attached to one other carbon. A secondary carbon is attached to two other carbons. And a tertiary carbon will be attached to 3 other carbons. What will be a quaternary carbon be attached to? How many carbons?
4.
4.
Will be, yes. It will be attached to 4 other carbons. Now, these are your multivalent atoms. Now, to multivalent atoms, we usually have these univalent atoms. For example, hydrogen or our halides, fluorine, chlorine, bromine, iodine, etc. Or a cyanide or a hydroxide, any one of these which is a univalent group or atom, you will just label them according to whoever's carbon it is. What does that mean? If you look in this example that I have right here, up here, this carbon, what is the classification of this carbon? This carbon is only attached to one other carbon, so it is a primary carbon. With that definition, any univalent group on it will be labeled according to this particular carbon classification. So this is a hydrogen on a primary carbon, and hence this will become a primary hydrogen also. And that is very useful for us when we will do more classifications. Can anyone tell me what is the classification, primary, secondary, or tertiary, for this purple carbon? Anyone? How many carbons are attached to this purple carbon?
Is it 1?
Only 1, yes, very good. What will be the classification hence? This will become a primary carbon.
Primary.
So if you look, there's a functional group on it. The hydrogens are there and the halide is there. These hydrogens are primary hydrogens. What will be the classification of this bromine then? It will be a primary bromine also. Overall, if you will look in this whole structure, you will label this structure as a primary alkyl halide. Why? Just because your halogen was on a primary location. Okay. So are you all able to see my page? Okay. If I have a structure like this, and remember, I'm not writing all my hydrogens, I'm just writing my carbons. You will have to understand, I hope by now, that which hydrogens are there and what all are missing atoms that I've not written here. So very similar to what we had earlier. This carbon, what is the classification of this carbon? Primary, secondary, tertiary, or quaternary?
Tertiary.
Tertiary. Why? Because it is attached to 3 other carbons, right? And so with that information, if I have a group on this carbon, the same carbon, instead of a hydrogen, remember there will be a hydrogen here for the 4th group. If I have a OH here, how will I classify this alcohol? What kind of a classification will I give it? For example, in the
alcohol.
Yes, very good. So for example, in the previous example that I was showing you, we have a primary alkyl bromide. But now, in this particular example, you have a tertiary alcohol. Or even if you don't know what this OH is, it's a hydroxide species. Don't worry about it. My main aim was for you to see that it will be a tertiary alcohol. Now, similarly, right here, same example I'm going to give you. What is this location? How will I classify this particular carbon? Anyone?
Secondary. Yes, secondary.
Mm-hmm. Mm-hmm. Armani?
Secondary.
Mm-hmm. Armani, are you here? Armani Pace?
Yes.
Armani, do you understand why is this a secondary carbon?
Yeah, because it's only attached to 2 other carbons on each side.
Very good, very good. So overall, it is attached to only 2 carbons. Very good. And that is why I'm going to label this as a secondary carbon. So if I have a chlorine here, how will I label this structure, Armani?
It would be a 2nd degree.
Mm-hmm. Secondary, what? Alkyl chloride.
Chloride.
Right? Okay, very good. Very good. Thank you. Any questions so far? So recognizing your primary, secondary, and tertiary are very important. Okay? So these are what the haloalkanes are. The alkyl halides, in broad terms, that's what we call them. And Rx is their general formula or the generic way by which we depict them. So remember what is R? RH. Oops. RH is a alkane, the general formula for an alkane. The R itself, by itself, is an alkyl. R with a halogen, chlorine, chlorine, bromine, iodine, will be your alkyl halide. Now, if you remember your module 1, there is an indication of covalent bonds. What are covalent bonds? When non-metals bond with each other. You can either have a non-polar covalent bond, for example, all the CC, CH, they are non-polar covalent bonds. There's no electronegativity differences. But there can also be polar covalent bonds. What does polar covalent bond means? There is a certain electronegativity difference. For example, this carbon and this chlorine. Chlorine is very electronegative as compared to carbon. So we draw the dipole, the arrow towards the electron attractor and the plus towards the electron loser. Any questions on why do we draw dipoles like this? So in your alkyl halides, we see certain polarity. And why am I insisting on you to know your polarity? When we will do module 4, we will be looking at boiling points and melting points and other characteristics and solubilities and stuff like that. At that time, the polarity, the dipole will help you. So this is the partly condensed structure. This is the bond line structure. This carbon is only attached to one carbon and hence it is a primary carbon. Any group attached to this carbon will become a primary alkyl halide. Similarly, this carbon is attached to two other carbons and hence it is labeled as a secondary carbon. Anything on this carbon will be a secondary alkyl halide. And remember how we're going to draw the dipole. Remember, we draw our sp3 carbons in a zigzag fashion or a valley hill kind of a fashion. And wherever you have to draw other groups, you will always draw wherever the point is. If the point is facing upwards, you draw your bonds upwards. If the point is going downwards, then you draw the bonds downwards. Question on how did I do my drawing here? Again, I just wanted to remind this to you from our module 1 class. This carbon is attached to 3 other carbons and hence it is a tertiary site. And any univalent group attached here will become a tertiary RX. So there are 3 further classifications of our alkyl halides. Okay. I want all of you to try and write the condensed versions of all of these groups. Go ahead, I'll give all of you 1 minute. And then I'll ask someone. So these are the 3 groups. Go ahead and write their condensed versions on your own papers. Okay. All right, anyone, any volunteers before I pick someone?
Yes.
Except
Yes.
Sammy.
Okay.
Yes.
Don't mind, Sammy, you are answering everything and I'm glad you are. But let's give someone else also a chance.
Okay. Thank you.
Okay,
I'll go.
I can do it. Oh.
okay, go ahead, Sydney.
For A, I got CH3, and then in parentheses put CH2 on the outside of the parentheses. I put a 2 on the outside because there's 2 CH2s, and then CH.
Very good. What about the third one?
The third one.
All right, the third one, yes.
Okay, for the third one, I put CH in parentheses. I put CH3 on the outside. I put a 3, and then I put CCl.
Yep, that's right. Good job, Sydney. Nelson, you want to try the second one?
Sure. Instead of doing the parentheses first, I just wrote the central. So I did CH in parentheses, CH3, 2, and then CO.
Okay, okay, that's good as well. So you can write this part both ways, like this also. So if you see this or this, they are exactly the same thing. These groups belong to the carbon before it. And since the parentheses start at the beginning, there is one of our exceptions. It will belong to the first carbon it is attached to. Okay, so both are correct ways of writing. Okay, very good, all of you. And even though Sammy did not answer, but you wanted to answer, so good. And all of the students who did not get a chance but wanted to answer. All right, so remember alkanes, haloalkanes. Oops, what did I do? And remember that there is a polar bond present in the haloalkane. And this is what is going to help you see other properties or characteristics that haloalkanes will have. Okay. The next group that we will be worrying about are the alcohols and the ethers. And so the general formula is ROH, and for ethers it is ROR. Now, how does this look like? Alcohols have to be classified primary, secondary, tertiary. And we saw a few minutes ago on my paper here how we can classify them, if they are tertiary or if they are secondary, and so on and so forth, right? So alcohols, alkyl halides, all of these need to be classified primary, secondary, and tertiary as well. In general, OH is known as the hydroxyl, based on the carbon bonded to the hydroxyl. So OH on its own is known as hydroxyl group. Now, alcohols can participate in the hydrogen bonding. This is something that is known, that when hydrogen is attached to an electronegative element. And what are electronegative elements that you know of? Oxygen, nitrogen, and all your halogens. All of them are, and sulfur, and so on and so forth. Whoever are your electronegative elements, and there is a hydrogen next to them, this hydrogen will become a electron or a hydrogen donor. This hydrogen will be able to do hydrogen bonding. And so because oxygen is a super electronegative element, the hydrogen next to it will be able to do hydrogen bonding. But this hydrogen bonding is missing in our ethers. Why is that? Because there is no hydrogen next to the oxygen in the ether. So what is the pattern that we see? For a regular alcohol, this is the pattern. So this is the carbon. This carbon would be primary, secondary, tertiary, or any other way in an aromatic system or anything. So this is the carbon to which your oxygen will be attached to, and then there will be a hydrogen. On the other hand, when you look at ethers, you will see that the oxygen is sandwiched between two carbons. So this hydrogen is missing in the ethers. Also important for all of you to remember is when you will have a system like this, what is the hybridization of oxygen in both of these cases?
SP2. Sorry, SP3.
Yes. Who does not understand why the oxygens are sp3 hybridized? Is there anyone who does not understand this? So
I have a question.
Go ahead. Mhm.
Isn't it sp3 because it's like single bonds, right? Bonded to the C and bonded to the H. That's how you can figure out if it's like a sp3, sp2, or
No,
sp.
we will figure those out based on the electron densities around it.
Okay, so it
Remember?
doesn't do with single bonds and triple bonds and all that.
So usually not all double bonds are sp2 hybridized. If you remember your carbon dioxide, these are double bonds, but is this carbon sp2? No, it's not. It is sp. Why? Because there are two electron densities around it. And that's how we know the two electron densities around it, or the hybridization around it. So you always have to know your Lewis structure first for the atom. When you know your Lewis structure, that there are two bonding pairs and then two lone pairs, then you count all the electron densities or domains around it. And then you will be able to figure out that if you have sp3 or what on your hand.
Oh, that makes a lot of sense. Okay, thank you.
Okay, very good. So with that knowledge, if you know that your oxygen is a sp3 hybridized element with a 109-degree angle, will you draw your bonds in a square box or like a zigzag? Like a zigzag. And with this piece of information, there will be a resultant dipole moment. Did you all see what I did? So this is not going to cancel out each other. This is not subtraction. They are in the opposite directions. The dipoles are in the opposite directions. Carbon is less electronegative. Oxygen is more electronegative. That's why the dipole is going towards oxygen. Hydrogen is less electronegative. Oxygen is more electronegative. And hence the dipole is going again towards the oxygen. In normal circumstances, if it were linear, if it was a square box, I would subtract these two. But because they are not pointing exactly in opposite directions, I will be adding these two to get a resultant dipole. Similarly, our pattern, even though if I'm writing it like this, I want you to remember your alcohols appear in a zigzag manner also. So generic formula for alcohols are ROH. We did a couple of questions, especially this example that I have shown you on the slide. this carbon, how will I classify this OH? I cannot classify this OH until I know what is the classification of this carbon to which the oxygen is attached. And then I see that my carbon to which the oxygen is attached has two other carbons on it. And so it is a secondary carbon and it is a secondary alcohol. That's how I will classify it further. And this is your bond line structure. Bond line structure, all the non-carbon hydrogens are usually marked. But if a hydrogen is with a non-carbon atom, we will always write it. Okay, we cannot just leave it like this, that okay, people will assume that there is a H next to it. Don't do that. Always make sure that you write your hydrogens with a non-carbon atom. So this is our alcohols. Remember this pattern, because when we will do our IR, this will be very, very useful for us. Ethers, on the other hand, are common organic solvents. So most of the reactions that we will see towards the end of the course will have some form of ether. Why? Because if you look at our alcohols, they have a great polarity associated with it. But on the other hand, your ethers, because this hydrogen is missing, there is no hydrogen bonding forming, they are easily released from the reaction system. So in this particular case, I have a symmetrical ether. So this is my oxygen, and on either side, I have a carbon. You don't have to classify ethers as primary, secondary, or tertiary at all. So this is a symmetrical ether. Why is it a symmetrical ether? Because whatever is on one side is exactly same on the other side. So a symmetrical ether. You can also have asymmetrical ethers. For example, how many carbons do you see here? 2. How many carbons do you see here? 1. So this side and this side are totally different. Now there is polarity in ethers also, and you will see a resultant polarity also. Okay, any questions so far? So there will be a resultant polarity here also, a resultant polarity here also. But there is a hydrogen bonding in alcohols. The hydrogen bonding is absent in the ethers. So in general, this is a pattern that you have to recognize in the structure. Remember, you will not be given straightforward structures. You will be given structures like this, or you might be given a cyclic structure like this. You just have to recognize that there is an oxygen with carbons on either side, and hence it is a ether. This is a cyclic ether, tetrahydrofuran. So there are 4 hydrogens, 4 carbons on this ring. Any questions so far from alcohols and ethers? Okay. Now, before I jump on to our carbonyl groups, I want to show you the amines. Okay. Now, amines are just like hydrocarbons, but there is a N group attached, not with any unsaturation. And I'll show you when you will see other unsaturation. So amines have nitrogen atoms attached to the carbon with no unsaturation. Can anyone remind me what is an unsaturation?
when there isn't as many H's as possible.
Very good. So usually there is a pi bond or a ring also associated with it. Okay. So if you look at ammonia, your nitrogen is connected to a carbon. Is there any unsaturation involved here? No. What about this nitrogen? This is nitrogen is connected to 2 carbons. Is there any unsaturation? No. This is connected to 3 carbon atoms with everything being saturated and no unsaturation. So that is the first thing that all of you need to remember when you're looking at amines. And you will see other nitrogen containing structures also. So don't get confused. Just have to worry about the carbon and the nitrogen. If you look at this example, there are other unsaturations, but we are not worried about those. So, in a structure, you will have many things. For example, you may have an aromatic moiety, you may have a CH2 moiety, and then you have an amine moiety. So you just have to focus and try to recognize what all groups you can see here. So just like carbons, nitrogens also are classified as primary, secondary, or tertiary. In our example earlier, I had these 4 carbons. Right? This is what I had earlier. So I'm just going to redraw them here. Okay. So instead of doing this, how about if I have something like this? How will I classify this structure? This structure will be classified as an amine, not as an alkane, not as a hydrocarbon, but as an amine. Why? Because there is a CN bond with no unsaturation. But then I also have to classify it. This nitrogen, based on this nitrogen, based on which amine I have been mentioning, this nitrogen is connected to how many carbons? Only 1 carbon. And so this is a primary nitrogen site or a primary amine. Okay. So 1, 2, 3, 4. And now I have my NH2 here. Who can tell me what is this structure? How will I classify it? What function group is this?
Amine. Secondary amine.
Why secondary, Sammy?
Sorry, this is primary because it's attached to 1 carbon.
Yes. So even though it is on a secondary carbon, the nitrogen, because of which we are labeling this as the amine, is still a primary amine. This nitrogen is attached to only 1 other carbon. And so this is still a primary amine. Now we have a amine.
Tertiary. Secondary.
So this nitrogen is connected to 2 other carbons. And so it is a secondary amine. So still no pi bonds or no unsaturation is there. And if you look at the example on the slide, oops, share my screen. If you look at this example right here, this nitrogen, all the carbons are saturated, so it is an amine. But what kind of amine is it?
Tertiary.
Tertiary.
Very good. So it is connected to 3 other carbons, and so I'm going to label it as a tertiary amine. So all amines need to be classified based on how many carbons are touching or how many carbons are attached to the nitrogen. Nitrogen has a very special property. It has a lone pair also. So with this, it can bond a fourth bond and can make
Quartz.
a quaternary structure also, but with a charge. On the other hand, carbon can just make it on its own because carbon can make 4 bonds. So this is a quaternary carbon right here. And this is a quaternary amine right here, but with a charge. So that is the only difference that we see between nitrogens and carbons. Any questions so far?
And that nitrogen you just drew would be sp3 hybridized.
So this was sp3 hybridized earlier, yes.
Okay.
It is still sp3 hybridized. If you look, 1, 2, 3, 4. It is still 4 parts, 4 domains. It is still sp3. But now it will be a proper tetrahedral because instead of the lone pair, now we have the bond. Okay. The next group of functional groups are the carbonyl compounds. Very, very popular organic materials. You will see them plenty times. Most of the carbonyl compounds will have this C double bond O. So at least HDI of 1 will be there. Now you need to be able to recognize them from their abbreviations and general structures also. So for example, if I write something like this, you should be able to see that there are 2 oxygens on the carbon. So this is something that we will have to practice a little bit more. So the first thing that we are looking as carbonyl compounds are aldehydes. These are the first carbonyls that we talk about. If you look here, and if you remember your alcohols have a general formula of ROH. What is the pattern that we see? We see a COH. But in aldehydes, we see C instead of the R. And then you see another C with the carbonyl, and the hydrogen. Okay, so this is our R group. This is the C double bond O part, and this is your hydrogen. So your R or the alkyl can be anything, right? Any of the hydrocarbons with 1 hydrogen missing.
I have a question.
Please go ahead.
How do you distinguish what's a butanol?
Butanol?
Yeah, like you see it says butanol on the side and it says 2-butanol. Like how do you know? Like that's what the structure is called? The butanol?
Oh, yes, yes. Oh, don't worry about that. Yes, yes. And yes, we will look at these nomenclatures very soon. But let's just focus on our aldehydes first. So if you look at your aldehydes and the structure that I'm going to redraw it. There is a CH3, CH2, CH2, C double bond O, and a H. Now this is the linear version. But what, let me draw another one. Let me draw a cyclic thing. Or if I'm being very clear about condensation. If you look at all of these drawings, all of them have the aldehyde in it. So this is and this and this are exactly the same. I just did not write the hydrogen here. So the aldehyde is always a terminal functional group. What does that mean? No matter how bulky or big a group is, your aldehyde would always be at the end of the structure. On the other hand, your ketones, you do not have a H here. So this is ROH or RCHO. So CHO just generally indicates you have aldehyde on your hand. But in ketones, you have the R, you have the C, the carbonyl, and you have the, instead of H, you have your R. Now this is very similar to what we studied for alcohols and ethers. Okay, I think I did not write it here. But alcohols are ROH, whereas your ethers are ROR. Now, instead of having just oxygen, or your aldehydes and ketones have been replaced with a carbonyl group. That is the only difference. So alcohols, ethers, aldehydes, ketones. You need to know their general formula so you can recognize them. And Sydney, if we go back to this structure, when you will study nomenclature, and we will look at this more closely, how we are numbering it. So there are 4 carbons. The carbonyl is closest, or the smallest value, smallest locant value when it is at the second carbon. And so we're just labeling it as the second bute because there are 4 carbons, and then this is the nomenclature for ketone. You don't have to worry about it. I just wanted to answer your question about that. Does this make sense, Sydney?
Yes, so 2 is labeled in front of it because of that oxygen that's attached to the carbon, right?
Mm-hmm. So if you look at this this structure, what is this group? There is carbon, carbonyl, carbon. Okay. And so this is a ketone. What kind of a ketone is this? This is 5 carbons, so it's a pentanone. At what location is your ketone? So we are just labeling the location here, at the 3rd location. That's all.
Okay, got it. Thank you.
You're welcome. So your aldehydes have a pattern like this. Your ketones will have a pattern like this. So the CH bond is missing in your ketones. Any questions so far? And just like our ethers, your ketones can be asymmetrical. This R group and this R group are different, or they can be symmetrical. Do you think this is a ketone? CCC, the COC pattern is still there. The C carbonyl C pattern is still here. Any questions? Okay. Now remember, this is all of these functional groups. You will have to memorize them. The carboxylic acids are our next group of carbonyl entities. And the pattern that we see here is R with the carbonyl group and then a OH. So far what we have seen R with a carbonyl and a H. What is that? Aldehyde. We have a R with the C double bond O and another R, which is a ketone. And then you have this, the carboxylic acid with the R, CO, and the OH. And as the name indicates, these are acidic materials. In fact, one of the first acidic organic materials that we had seen were the carboxylic acids. You know about the hydrochloric acid and the H3PO4 and H2SO4. All of these are mineral acids, or the general chemistry acids that we have been using in general chemistry. So carboxylic acids are actually the first bridge from the inorganic acids to organic acids. And we will be looking at acids in much detail starting Monday. So the carboxylic acids, the functionality, again, there is a lot of polarity involved in this particular setup. If you look at your, if you look at your carbonyls in general have polarity associated with them. But the carboxylic acids have a hydrogen also, which can do hydrogen bonding. So this is a speciality that you have to remember, because this hydrogen is attached to an electronegative element. So there's polarity here, and the polarity right here. Just like your aldehydes, your carboxylic acids are also always terminal at the end of your reaction, or at the end of the structure, either on this end or on this end. They will always be at the end of the structure. Now the carboxylic acids have their own derivatives, and these derivatives on slides 15 and 16, I'm going to rewrite them a little bit on my paper. Okay. So let's say that I have a carboxylic acid. From this carboxylic acid, I can make, using all of this part, few other functional groups. Now if you look 1, 2, 3, remember this carbon of the carbonyl, I'm also counting that carbon. 1, 2, 3, 1, 2, 3, 1, 2, 3. If to this R group, okay, so this is that R group, I have a OH next to the carbonyl, I label it as a carboxylic acid. But if next to this R group and this carbonyl, I have a OR kind of a group. So instead of just writing R, I'm actually giving you a reasonable structure. So what is the pattern that I see? I see C double bonded O and a oxygen. This is the pattern that I will see. These are known as esters. If instead of just carbonyl, I have a group like this. C carbonyl, oxygen with the carbonyl. So between two carbonyls, I have an oxygen. This is known as a anhydride. And instead of all this, if I just have a RCOX, let me just write L. This will be an acyl halide. Any questions on what I just did?
So basically, you're just adding R groups at the end to show that it could turn into an ester, anhydride, or acyl.
Acyl halide, yes. So all of these are derivatives of carboxylic acid. Carboxylic acids can in fact make other derivatives also. And let me quickly write those for you as well. So I'm going to use the same carboxylic acid and I'm going to make a So instead of just writing R or H, I have actually given you an example. All of these are known as amides. So I should have written it here. This is my carboxylic acid. And these are amides. What do you see here? There is a carbon-nitrogen bond, but there is some unsaturation on this carbon. Okay, so is this a amine? This is not an amine. Amines do not have unsaturation on either the carbon or the nitrogen involved in the amine. There might be unsaturation away from the molecule, but not in either of them. So this is a primary amide. Why? Because this nitrogen is attached to one carbon. This is a secondary amide because this nitrogen is attached to two carbons. And then you have a tertiary amide as well. 1, 2, 3. Any doubts on how I got these? You don't have to know what is the reaction going on, but I just wanted you to see that what is the general formula. There is a R, so there is this carbon, and then nitrogen. This is the common pattern that we will see in all the amides. In all the amides, we are going to see this pattern. But a primary amide will have RCO. Remember, we were writing the condensed structure, condensed formula, and then NH2. RCO, N, H, R prime. So why did I write a R prime? Because I don't know what this group will be. It may be same, it may be different. These two are groups. So this is a R group right here, and this is a R prime group right here. Any questions on what I was marking just now? So in here also, this is my R group, and these are my other two R groups. So I will write them as R, C double bond O, N, R, R prime, R prime, R double prime. Just indicating that they may be same, they may be different, but there are some alkyl halides present here. The last carboxylic derivatives that we see are nitriles. Now you will say, how are these nitriles carboxylic acids? Now I just want to indicate to you, to a carbon, when you have a unsaturation with electronegative elements, we usually call them or they usually belong as a carboxylic derivative. When you will hydrolyze all of these derivatives, when you will add water and a little bit of acid to all of these, they will generate starting ester. And that is an indication so hydrolysis. What does lysis or lysis means? To cleave or to cut. So nitriles, amides or amides, esters, anhydrides, and acyl halides. All of these are your carboxylic acid derivatives. You need to know and be able to recognize their pattern and know if they are ester, anhydride, acyl halide, amide, or a nitrile.
Wait, I have a question.
Go ahead, Daj. Dihar. Yes.
For the amides that are derivative of carboxylic acids, they're only, we call them amides because of the unsaturation, right?
Amides, yes, yes. And this pattern, the CONH or the CON pattern, you see there is this carboxylic acid, and we will learn amides in detail. This part, even though this nitrogen is sp3 hybridized, this part is actually a flat part. And this part is the basis for the formation of all the peptides and all the proteins and part of our DNA also. Just because of this carbonyl oxygen, and we will see in resonance that it creates something like this. Okay. And so this part is always a flat, planar structure. So there is some an unsaturation between these two atoms because of that resonance. And so whenever you're looking at amines and amides, always know your amides between the CN bond, there should be no unsaturation. If there is unsaturation of any kind, you cannot have amines then. It will be some other nitrogen containing compound. Does it answer your question, Nihajia?
Yes, ma'am. Thank you.
Okay, very good. Okay, so we did the acyl halide and the anhydride. And if you look at the anhydride that I had made, okay, there is this pattern of carbonyl, and oxygen sandwiched between those carbonyls. That could be in any shape or form. Okay, I can do this also. This is also an anhydride. Why? Because the oxygen is sandwiched between two carbonyls. Any questions so far? Okay. Now the last group that we will be looking at are the sulfur containing compounds, and we will just be looking at the thiols and the sulfides. The thiols are a derivative. So if you know your periodic table, oxygen and sulfur, they are in the same group. If you replace oxygen and place a sulfur, that's what a thiol is. What is an alcohol? Alcohol is ROH. What is a ether? It is ROR. So we are just replacing the oxygen with a sulfur. Now usually the sulfides are also called as thioether. So you must have guessed that thio has something to do with the word sulfur. So these sulfur-containing compounds are the only kinds that you will be, or we will be using them. And they're very stinky compounds. So in general also, the labs or laboratories or research labs also do not want to work on them. Okay, very quickly, let's look at the functional groups here. So you will be given a very different kind of a structure and you will have to figure out what all functional groups are present here. So remember, alkanes are not considered as a functional group. So what we have here is a carbonyl. What kind of a carbonyl? This carbonyl has carbons on either side, plain sp3 carbons. And so this carbonyl is a ketone functional group. If you look at this particular structure, remember there is an overall spread of electrons. So this overall spread of electrons is lending the aromaticity to our structure. Remember, benzene is one of the only structures that you have to know as an aromatic structure. Now in this particular structure, you do have nitrogen, but look at all the carbons. Is this nitrogen and the carbon at all locations completely saturated, or is there some unsaturation somewhere? There is some unsaturation somewhere. So you cannot call it a amine. You have to call it a amide. Any questions so far? Okay. Oops.
Because of that double bond, right?
Yes, because of that
amide.
unsaturation, yes. Okay. I want all of you to copy the following structures, which I'm going to make. So this oxygen is within this ring. There are 5 carbons and 1 oxygen. Go ahead and draw these out because I will be changing my screen in a minute. And please make sure that you label them A, B, C, D also. Is there anyone who did not copy these yet?
Me, I'm still writing.
Okay, go. Okay. All right. I'm assuming all of you are done completing this. So I'm going to go ahead and give you a poll. Among all of these structures, among A, B, C, D, which you have copied on your paper, which of the structures is a ketone? And you can look at your notes for now, of course, and look back and tell me what is among A, B, C, and D your ketone. All of you will have 1 minute to answer this question. 10 more seconds. 7, 6, 5, 4, 3, 2, 1. Okay. And most of you got that right. Out of the 14 students who attempted the poll, 12 of you did say that this D is our ketone. And that is the correct thing, because you have to look at the pattern. So what is this functionality right here? This functionality with the carbonyl O, this is like a RCOOR kind of a functionality, which will be an ester. This 2 carbonyls sandwiching a oxygen will be your anhydride. And this oxygen sandwiched between 2 carbons is a ether. Now on your exam and on your drill, you will be given a big structure where the functional groups will be there. So I want all of you to copy it, look at it, and tell me by Monday, how many functional groups and which all functional groups do you see in this particular structure? So make sure that you copy this structure out correctly. Okay. All right, anyone still copying the structure? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, very good. All right, so we're going to go ahead and do our last part of this chapter, which is molecular spectroscopy. It is in chapter 14 for climb, but we have to introduce this here because spectroscopy is very important part of our course because it'll help us investigate molecular structures. Now, the only thing IR is going to help us with is the functional group determination. Okay, and how is this going to happen? Now, in your lab also, if you have done the lab, you will see that you will take a little bit of sample and you will just place it in the machine and you can retrieve your IR back, IR sample back. So it is a non-destructive method. But how is the infrared spectroscopy going to help you? The IR region is between visible and microwave region of the electromagnetic spectrum. And for all our information, it lies between 400 to 4,000 range. Now on this very chart, I wanted to explain to you what does this mean for us. Oops. Now, if you look at the wave number or if you look at the wave numbers that are indicated here, what is a wave number? A wave number is number of waves per centimeter square or per centimeter. Let's imagine there is a box with the area of 1 centimeter. If you can pack 5 waves, let's say, in one box, or if you can pack 10 waves in that 1 centimeter square box, who do you think will have more energy? Where you have more waves. And that is what is indicated. The more waves there are felt, the higher that energy will be. So this part of the graph indicates more energy required to vibrate the bonds, whereas less energy is required to vibrate the bonds on this side of the graph. Now, when we look at all our bond types, between 400 and 1300, you will see single bonds. Now, we usually label this place area as fingerprint region also. And the only peak type that we are going to look at it is the C single bond O. Now, there will be other peaks present here, but you don't have to worry about any of them. You have to learn how to ignore other peaks. The only peak that we will care about is a peak between 1000 and 1300 centimeter inverse. It will be a strong and broad peak. So all the single bonds, except all the hydrogen bonds, will be in this region. The next region is for your double bonds. This is between 1600 to 1800. Next is your triple bonds, which is between 2100 to 2300. And the last part is the hydrogen bond. If you think about it, you need more energy to vibrate, which has hydrogen bonding present in it, right? So we were talking about hydrogen bonding, and the same molecule will be bonded almost twice. So it'll take more energy to vibrate these bond types. And so they appear higher in energy or at a higher wave number. So all the electronegative, the OH, the NH, and the SPCH, they appear in the region 1. Region 2 has CH bonds, but sp3CH bonds and sp2CH bonds. So if you think about the IR spectra in general, this is what the IR spectra will have. This is where all the bond types will appear. So on your spectra, you will see a peak. Let's say you see a peak here, and then you see a peak here, and there are many other peaks, and then you see a peak here. You will have to learn first to ignore non-essential peaks. You will only be looking at special regions, specific regions of the IR spectra to figure out that a peak is there. So this is a relevant peak, a good relevant peak, a good relevant peak. So from our previous information, what we just studied about, this is probably a single bond, which is not a hydrogen bond. So how many single bonds do you know of? Right? So there are so many of them. The only one that will actually appear in this region is the C single bond O. Similarly, in region 2, if you see some peak, you know it is either a sp3CH, which is 99% present in all the organic compounds, or a sp2CH peak. And then this part, the round portion, comes from the OH. And this is something that I'll tell you in a minute. But for all of you, for your information, we got 3 bond types. When you know that you have these 3 major peaks, and you know that you have these 3 bond types from the IR graph, then you put a puzzle piece together and you say, okay, the C and the O are connected, and the O and the H is connected, and the C is connected to probably a hydrogen. So this is the sp3CH. And what is this pattern? What is this functional group that we have been talking about a few minutes ago? This is a general formula from alcohol. So whatever spectrum we are seeing right now belongs to a molecule who is a alcohol. Did you see what I just did? Or any questions? Don't worry, this is just the first time that you're looking at it. You don't have to be super scared of it. So all of your alcohols, if you have a 1-OH or if you have a branched structure, super branched structure, both of these structures have the general formula ROH, ROH. And hence, both of these structures will have the same IR spectrum. That is the only limitation of your IR spectrum. The IR spectra will definitely give you the functional groups. You will have to list out all the bond types. So for example, in this structure, what are the bond types that we see? I'm going to expand this out to help me see. So what are the bond types that I'm seeing here? I'm seeing a C single bond C. I'm seeing a C single bond O. I'm seeing an O single bonded H. And I'm also seeing sp3CH. Now there are several sp3CH. I'm not going to point out all of them. Even if one of them is there, it will appear on my IR spectrum. If I look at this structure and I want to list my bond types from this structure also, what are the bond types that I will get from here? I will certainly get my C single bond C. I will also get my C single bond O. I will also get OH. And what else? All of these carbons have hydrogens on them. By the way, all of you, do you know what is this? What is this group? Anyone? Is this a hydrogen or is this a carbon?
Carbon.
Carbon.
This is a carbon with 3 hydrogens. So this is a methyl group. So I also have sp3CH. Is there any other bond type that I missed from this? So both of these structures are the same functional group. Even though this is a primary alcohol and this is a secondary alcohol, it still did not affect the IR of this molecule. Both of them will have the same IR spectrum. Now, why do we see the IR spectra and how is it dependent? There is a thing called peak strength or bond strength and bond polarity. So let me ask you again, who will be more polar, C single bond O or C single bond N? Who will be more polar? How do we decide polarity? We decide polarity on basis of electronegativity. So oxygen is more electronegative, so it will be more polar than CN. And this is something that we will see on our IR spectra also. The more polar will have a higher intensity. Intensity can be strong or intensity can be weak. So more polar will have stronger intensity. Another thing that can define your IR peak is the shape of the peak. So this is for the peak, shape of the peak. The shape of the peak can be broad if it is more polar, or it can be sharp So for example, if you have C double bonded C and you have a C double bonded O, who is more polar in the double bond? The C double bond O is more polar. So it will be more broader. Whereas in the same region, if C double bonded C is there, it will be less polar. It is actually non-polar and it will be sharper. Weaker intensity and sharper. That's what C double bond C will be. Remember, I was telling you that in one region you only have double bonds. So both of these peaks can appear in that same region. But for your course, we will only give you one structure at a time. But you will have to look at the peak if it is strong or broad, and then discuss that, point out that. And then the location of the peak. So this is also something that we did. That is dependent on the bond strength. If you have a hydrogen bond, the peaks will appear somewhere near the 4000 region. If the peaks are single bonds, the peaks will appear near the 400 region. And usually the IR is covered extensively during the laboratories. I'm not sure how many of you have lab this summer, but I have a packet here which is from the lab, and I also have in the drill section some extra information that I would like all of you to look at. The IR discussion. These are like 8-10 minutes videos that all of you can look at. So this is what I usually teach to my lab students also. So Organic Chemistry 1 drill, it is under the IR discussion. Now I know we are almost out of time, but I quickly want to finish up this module by giving you a little bit more information about the IR. So for your course, you just need to know these ranges. So let's say that I say that there is a peak between at 3400. When I say there's a peak at 3400, you should know that it is either at for the OH, NH, or the carboxylic. That is in region 1. But how does the peak look like? And this is what I have shown you here. The NH peak will be a medium-sized peak. Okay, because of one hydrogen, you will have single pointed. Because of two hydrogens, you have this double pointed. Between NH and OH, OH is more polar, and hence you see a broader peak appear in region 1. Furthermore, when you have a carboxylic acid, the carboxylic acid will cover region 1 and region 2. So remember, this is the region where your hydrogen bonds appear. In region 1, you have the OH, NH, SP, CH, whereas in region 2, you have sp3CH and sp2CH. Between 1600 and 1800, you have this strong peak. And we had just compared that between C double bond C and C double bond O, C double bond O is more polar. So the stronger peak will be from the carbonyl. And between, you don't have to always look at the fingerprint region. Always start to read your IR spectra from the left-hand side. So in this particular region, between 3200 and 3600, a peak is appearing. This peak is appearing right here. This is a multi-pointed peak. which belongs to sp2ch right here. And then sp3ch peak. Now, usually when you have a multi-pointed peak and a small peak appears like this, that will belong to sp2ch. The bigger multi-pointed peak belongs to sp3ch. So make sure that during this weekend, you look more at these numbers, especially the functional numbers, the frequency ranges. What are the shapes of these peaks in different regions? And you should focus majorly on carboxylic acids or your alcohols and your ketones. You will be just getting the peaks or the bond types. You have to put a puzzle piece together and figure out what is the actual functional group that we can derive from here. Okay. Any questions?
Can you check the chat, please?
Okay, hold on. We don't have drill today. Okay, but what we will have is a quiz in a minute.